All right, welcome everyone to another seminar on geometry with or without symmetries. And today it's my pleasure to introduce Marco Radeschi from the University of Notre Dame, and he'll be talking about invariant theory without groups. So thanks, Marco.
Thank you, Ramiro, and thank you to all the organizers for letting me speak here. What I want to talk about is essentially a work that I have done with several co-authors, essentially developing this weird concept of invariant theory where groups are taken out of the picture, but you can still recover a lot of things that can be applied in nice settings. So let me start by just mentioning what it is the invariant theory I am going to look at, and trying to generalize. So the invariant theory is the following. I'm looking just as a representation of a compact group by isometries. So it's an Euclidean space, and G acts by linear isometries. And given this representation, we can associate a ring that is the ring of those polynomials that stay invariant under the group action. Or if you want, you can also think of it as the polynomials that are constant along the orbits of the group action. And the point of invariant theory is to study representations and actions in general through the analysis of the algebraic structures of the algebra of invariants. Now, already here there is just this very small remark that because of the way it is defined, it could be, you could see that the situation where you may have two different group actions that are still orbit equivalent in the sense that they have the same orbits. And of course, since the polynomials, the ring of invariant polynomials is just defined as polynomials constant on the G orbits, well, the G1 and G2 invariant polynomials are going to be the same, essentially because they really do not depend on the action itself, but rather on the decomposition into orbits that they generate. And this already leads in the direction that I want to bring the conversation, because the idea is to remove the group from this whole picture. Now, before removing it, just a quick just a remark that if you have an orthogonal representation, then the group G acts on the unit sphere of V, which I from now on will denote just by SV. And we have a couple of things. First of all, again, the moment G is a closed group of isometries, then the quotient space gets the structure inherits the structure of a Hausdorff metric space, where we define the distance between 2 points in the orbit space to be just the distance between the actual orbits in the sphere. And we can define a map. This is just a map that takes a point to its own orbit. And this map has fibers that are smooth because, well, the fibers are just the orbits of the action, and they are equidistant, if you want, essentially by the fact that their distance is constant. So equidistant here, I mean just that for any two orbits, the distance between the two orbits does not depend on where you look, on which point you look, on which point you measure the distance from in one orbit to measure the distance to the other. And these two essentially, the whole idea of removing the group is to replacing the orthogonal representation with a map that has exactly these two properties here. I'm going to just do it a little bit more generality for general Riemannian manifolds. I say that a manifold submetry is just a map from a Riemannian manifold to a Hausdorff metric space whose fibers are smooth and equidistant. And if I want to look at a specific case of actually maps from spheres, then I will refer to this as a spherical manifold submethod. Now, this thing here is, this is one way to get to them, but just as like, oh, what if we remove the group? But as a matter of fact, these things, these manifold submetries and spherical manifold submetries are rather natural. They appear very often. They generalize a number of things, well, orthogonal representations, as we just discussed, but also Riemannian submersions, other objects called isoparametric submanifolds that I'm not going to define because they're not important to our discussion at least, and the singular Riemannian foliations with closed leaves. Now, this is true for all manifold submetries. And within manifold submetries, the spherical ones, so manifold submetries from round sphere, play a special role because they, in a very specific sense, establish, so spherical manifold submetries are actually represent the linearization of a general manifold submetry at a point. So essentially, they give you information about the local structure of a general manifold submetry at a point. Also, they are conjecturally expected to appear whenever one has a sequence. So again, this is a conjecture that says that if we have a sequence of a manifold a sequence of a Riemannian matrix on a, let's say on a fixed matrix space, on a fixed Riemannian manifold. And let's say that this sequence has a uniform lower bound on sectional curvature, let's say non-negative sectional curvature, and the sequence collapses. So it converges in the Gromov-Hausdorff sense to a matrix space of dimension strictly lower. Then the conjecture is that this collapse occurs somehow along the fibers of a manifold submetry. So the idea, the conjectural behavior of this collapsing sequence is that you secretly have a foliation of your manifold where the fibers are getting contracted to a point, and your bigger manifold is contracted to something of smaller dimension. Again, this is just a conjectural, but in several cases, like in this simple case in which this conjecture has been proved, well, this turns out to be exactly the behavior.
So Marco, maybe
Yes.
you'll mention this later, but could you give an example of this happening with unbounded sectional curvature?
Can you say it again?
Because,
so,
I mean, if
yep.
sectional is bounded, then the collapsing occurs along infranil manifolds, right? Which I guess the very special.
I guess that would be the idea. Yes.
Yeah, but what if?
Not really, right? Right now, I'm not asking that the sectional curvature is bounded above and below.
No, that's what I'm saying, right? So if it's bounded above, then that's Chigger-Fukaya-Gromov
right
theory. But can you give an example where sectional is unbounded above, and you to have a feeling of what the fibers would look like? Or
so when you do not have the bound above, well, yes. So just pick a how do you say, a Chigger deformation, right? So you have a manifold with a group action, right? And you apply the Chigger deformation. Essentially, that is contracting all the orbits to a point. The orbits are not infinite manifolds in general, right? So you're not going to get a lower, like a common upper bound of curvature. Did I answer your question?
yes.
Good. Okay, so right. The goal, primary goal for, well, that would be very nice to have, to reach, is to have a complete classification of these singular manifold submetries, which again is going to give a complete understanding of the local structure of what these manifold submetries can look, and which again is going to give structural results for a bunch of situations in which these manifold symmetries appear naturally. Unfortunately, this goal is at the moment far from being reachable. Even the classification of spherical manifold symmetries of codimension 1, so spherical manifold symmetries projecting down onto the simplest possible metric space that is not a point, so an interval, it turns out that this problem here is equivalent to classifying what are called isoparametric hypersurfaces. And the study of isoparametric hypersurfaces in sphere is a very old subject that started back at the end of the 1800s. Well, no, it was actually the beginning of the 1900s. And then it was actually got picked up by Cartan that started the classification. And this classification has been going on. And essentially, the classification is almost complete, but there are still a few special cases missing. That's the point. So even in the simplest case, we have a century-old story that is not entirely complete. So of course, we cannot expect to just go there and classify the completely general case by replacing the interval with any Hausdorff metric space that you can have there. So we can get to the second. What did I do? Okay, we get to the second best thing, that is produce examples. So try to get as much as possible. On the one hand, producing new examples and constructions, and on the other hand, trying to produce structural results that limit the amount of things that you can imagine possible. And until possibly the two directions coincide and you get exactly a full classification. This theorem here I added just because I'm talking about structural results for spherical manifold symmetries. I cannot not mention this recent theorem by Kapovic and Lichak, where they classify, they essentially did a very similar thing to what we're doing, but in the more general case of submetries. So these are just maps in which fibers are equidistant, but not necessarily smooth. In their case, they proved some nice results in terms of like a regularity of fibers being C11 manifolds, possibly with boundary, and the structure of the quotient being an Alexandrov space with curvature bigger than or equal to 1, with a nice stratification. It doesn't, we're not going to use these things. I just wanted to mention that there is some nice classification already before adding the information of the fibers being smooth. I will not discuss this further. The interesting thing is that adding smoothness here improving the submetry to a manifold submetry with smooth fibers, you may think, oh, then I'm going to essentially get a better result in the sense of like replacing some of the structural results to some smooth versions of this. Well, it turns out this is not the case, and asking for smooth fibers implies extremely strong conditions on what the fibers and what these spherical manifold submetries are going to look like. So I decided for time reasons not to go over the part about the known examples and constructions. What you should know about it is that we don't know many. We know what are called the homogeneous manifold symmetries. So the manifold symmetries that just come from quotients of orthogonal representations. And there is another family called the Clifford foliations that are mostly non-homogeneous. And essentially, these are the only two known building blocks for spherical manifold symmetries. And then there are two different types of constructions that take different manifold symmetries to produce new ones. But the idea is that there is really not much known out there. It is not even known if that's all or not. Probably not. But whenever there was whenever somebody would look at a specific subclass with the idea of classifying maybe a subclass of spherical manifold symmetries, the only thing that would come out of a classification would be only the ones that are known. So there is a big question mark between the few examples known and the few and the nothingness of structural results that were present up to a few years ago. To my knowledge, the first structural results comes from some results of mine with Alexander and then with Ricardo Mendes that essentially tell us that spherical manifold symmetries actually have an algebraic nature. So in order to understand the how and why, let me just give a quick definition. So given a spherical manifold symmetry, let me denote by B of sigma the algebra of those polynomials that are basic. And basic just means constant along the fibers of the manifold symmetry. So essentially, these are polynomials that descend down to the base of the manifold symmetry. And here is the theorem that we proved again with Lichak for singular Riemannian foliations and then extended it with the Ricardo for general spherical manifold symmetries, that essentially says, first of all, let's go through this line by line. So the first thing is telling us that this algebra of basic polynomials is finitely generated. So there are only a finite number of polynomials. Actually, yeah, these should be generators really in sigma, not just polynomials, but a finite number of polynomials of basic polynomials that generates the whole algebra. And the second thing is that if we take these polynomials and we stick them together and produce a polynomial map that takes a point P to the point rho 1 of P dot rho K of P, and let's say that the image is X, then what happens is this. So on one hand, we have our spherical manifold symmetry we began with. In here, we have an algebraic map. And at the bottom, we have a homomorphism that makes the whole diagram commute. In particular, what it means is that the fibers of the algebraic map are the same as the fibers of the spherical manifold symmetry, which means that, well, the fibers, and here's this, the fibers of sigma, of our original fibers, are actually algebraic varieties, and they're given by the level sets of these polynomials that we have. So these essentially, oh yeah, here I just wanted to remark that if we have a homogeneous, the moment we have a manifold symmetry just coming from a straight quotient by a group action, so there is some symmetry in this talk. The set, the algebra of basic polynomials just is the algebra of invariant polynomials. Okay, so essentially, again, we are studying the algebra that is just the algebra of invariant polynomials without the group acting in general. Now, the idea here is that this gives a nice way to move from this metric problem of spherical manifold symmetries into an algebraic one. It produces a map from spherical manifold symmetries to algebras. And it would be great to have a map that goes back, because, well, if we had a map that goes back, we would have maybe a way to transport our problems in, like our geometrical problems, into algebraic ones, manipulate them somehow using algebraic tools, and bring them back and maybe like produce new foliations, new spherical manifold symmetries, or maybe new structural results that at the level of spherical manifold symmetries. And indeed, so this can be done before one has to I need to define this concept of Laplacian algebras to be just, we say that an algebra of polynomials is Laplacian if, first of all, it contains the quadratic polynomial given by just the square distance from the origin, and also if it is preserved by the Laplacian. Okay, for every element in the algebra, the Laplacian of the element is also in the algebra. And it is very easy, well, it is one of the results is that the algebra of basic polynomials of a general spherical manifold symmetry is always a Laplacian algebra. So what we can do is we can, okay, maybe instead of looking at all the possible algebras, we just want to look at Laplacian algebras. And here's the thing, the moment we add this condition here about just looking at Laplacian algebras, then a theorem essentially stemming from a couple of results of mine with Ricardo says that these two categories are in fact equivalent. And we have actually functors that move from one category to the other, one of them being just the functor that takes a spherical manifold symmetry and associates a Laplacian algebra. And then, well, here is the result. We, for every Laplacian algebra, we can construct a spherical manifold symmetry out of it. So for every Laplacian algebra, actually, there is a spherical manifold symmetry. And in fact, the way we constructed it is that it really represents an inverse for the map P. So the map L and B kind of represent an equivalence between the two categories, which is exactly what we want. And previously we used this result here to prove a number of we applied this result to prove a number of results in classical invariant theory. So the idea was to just essentially start with a representation on the left, right? Start with a representation on the left, and well, study the algebra that we got here and get information about the original representation. But today I do not want to talk about this. Today I want to talk about some recent result with Ricardo and Samuel Lin, essentially where we use this information to actually get information about the geometry of these spherical manifold symmetries, and more importantly, about the geometry of the quotient space X, of the base space X. Before we get there, I actually want to be a little bit, I want to just open a parenthesis if you want, although the parenthesis itself is rather important. And we will get back. So I'm going just to put on hold for a moment this invariant theory without groups. By the way, before I get to this, let me just say, when we talk about invariant theory without groups, this is what we are referring to, is the study of the geometric properties of spherical manifold symmetries via the study of the corresponding Laplacian algebra. This wants to be the area in which we move. So what I wanted to quickly discuss is this, the fact that we can actually do some spectral geometry on manifold symmetries in general, not just spherical manifold symmetries. So let me just give a couple of definitions here. Given a manifold symmetry, there's a fact that we can find an open, dense, convex, smooth Riemannian manifolds inside of X. So this is already saying that this quotient space, so the base space of a manifold submatrix is not just a generic space, but it contains an open, dense, convex subset that is a smooth Riemannian manifold. And when you restrict the manifold submetry to the preimage of the set, this is actually a smooth Riemannian submersion. Okay, so this is actually a Riemannian submersion almost everywhere. And we say that this manifold submetry has basic mean curvature if the mean curvature of the fibers, remember each fiber, so through each point you have a unique fiber, and so you can associate to each point, especially to each point in this irregular part, you can associate a vector that is the mean curvature vector of the corresponding fiber to the point. And at least again in this M0 part, okay, which is again open, dense and whatnot, in here you actually produce a smooth vector field that is called the mean curvature vector field of the manifold submetry. And we say that again, the manifold submetry has basic mean curvature if this mean curvature vector field projects down to a vector field on X0. You may be wondering, okay, how spatial this is. Maybe rather spatial, but there are classes of like a bunch of situations in which we know that this is satisfied. We know that a manifold submetry has basic mean curvature, for example, when it is homogeneous, so it is coming from a group action, or when the manifold is a sphere. It's actually more general than this. I believe that anytime you have a symmetric space, so any manifold submetry from a compact symmetric space should always have a basic mean curvature. But that's not the point. The point is that although, again, this condition is rather spatial if you consider all the possible matrices, when you restrict to nice matrix, fairly symmetric, then this should just occur. And the point is that as one of the ingredients in the algebraicity theorem that I was mentioning before is the fact that you have averaging operators for this type of spherical manifold submetries. Let me tell you what I mean. So the moment you have a manifold submetry with basic mean curvature, then you have an averaging operator. This operator is an operator that takes L2 functions to L2 functions that are constant along the fibers, almost everywhere. And this operator really behaves like the nice averaging operator whenever you have a group action where you take like a function and you average it over the group. In particular, this averaging operator commutes with the Laplacian, and it induced a map from smooth functions to smooth basic functions. So this operator, again, the averaging of a smooth function is again a smooth function. And the neat thing that is going to be very useful is that it commutes with the Laplacian operator. And okay, I just rewrote the same theorem here. The fact that you have this property of the averaging operator commuting allows to say that the Laplacian of the manifold restricts to just, I mean, you can define the restriction of this Laplacian acting on basic functions. And what happens is that you have a spectrum for this Laplacian, which is a subset of the spectrum of the actual Laplacian. So now you have this operator here, which has its own eigenvalues, a subset of all the eigenvalues of the Laplacian, and it has its own eigenbasis, which is again a subset of an eigenbasis, of a basis of eigenfunctions for the original Laplacian. And it's not really a problem, but you can imagine that what you would like to do with this at this point is to somehow relate the eigenvalues of this operator with the geometry of X, right? So in usual spectral theory, you relate the eigenvalues of the actual Laplacian with the geometry of the manifold. In this case, we want to relate them with the geometric properties of the quotient. And this brings me to the recent work in progress, joint with Ricardo Mendes and Samuel Lin, to which I owe a great, I think we all owe a great debt to Emilio that suggested the very nice, suggested us to look at the very nice papers that gave us good indications on how to attack the problems that I'm going to just read, which is in here. That is the foliated vials law, or the, foliated version of vials law that says exactly the following. We start with the manifold symmetry with basic mean curvature, and we look at the eigenvalues of the basic Laplacian. So of this operator, right, of this Laplacian are restricted to basic functions, and we look at the we only look at the number of eigenvalues up to a certain point, up to a certain values, and we look how this number goes to infinity as we let t go to infinity, and we look at this behavior, and the behavior is the same as the usual Vials law, where it says that this function here just behaves like a function, like a power of t, and the exponent is half of the dimension of the base, and the coefficient has to do essentially is a universal constant times the volume of X. So these essentially the idea is that you can read off the volume of the base of a manifold symmetry out of this asymptotics of this asymptotic number of eigenvalues of this Laplacian. Again, this fact that was proved in the case of again in the homogeneous case where we are dealing with the group action. This was proved by Donnelly and separately, but pretty much at the same time, by Brüning and Heinze. Their results go a little bit more in depth, because the moment you have a group, you have a representation theory, you have a bunch more stuff that you can look at, and they do, and they produce something a little bit more general, but in the case in the more general case where you remove the group action and you just define the manifold symmetry with basic mean curvature, well, you still get essentially the same result. That's the point. So this is the first of a couple of results that allows us to estimate geometric quantities of the geometric quantities of the base X in terms of eigenvalues. Once again, thank you, Emilio, for pointing out this paper to us. It was very, very important. The other thing is to do with the estimating the diameter of the quotient. Now, this is a little bit less remarkable than the Vials law. The Vials law really tells us like how to compute the volume the moment we know these asymptotic, these eigenvalues, how they grow. The next result really only gives us some bounds on some estimates on the diameter, but I guess it is still something. In here also you have to add the requirement of non-negative Ricci curvature, and what you get out of this. So once again, the moment we have a manifold symmetry with basic mean curvature, then essentially a foliated version of Li Yao says that the diameter of the quotient is bounded by pi divided by 2 times the square root of the first eigenvalue of the basic Laplacian. And the foliated version of Chang theorem gives us an upper bound on the diameter, which unfortunately depends on the dimension of the manifold itself, which is not great because we would like to have things only depending on the quotient and only the quotient. This is not it, but it's still something that some positive result in some positive direction. So this wants to close with this. I close now this parenthesis about the spectral geometry for spherical manifold symmetry, and I go back to the invariant theory without groups. Okay, so I'm moving back to the case of spherical manifold symmetries. What can I get from there? Again, I have a spherical manifold symmetry, and I take A to be my Laplacian algebra. Now, it turns out that the Laplacian algebra is always a Cohen-Macaulay algebra, a Cohen-Macaulay ring. It doesn't really matter what it means. The point is that it can be written like this. You can describe the algebra in terms of 2 types of generators. One is the generators F1 through Fq. These are algebraically independent polynomials. So this really is a free algebra on Q polynomials. And then essentially you have other, they're called secondary generators, secondary invariants that describe completely the algebra. And right, so what we know about these polynomials is that, well, the first polynomial in F1 is just R squared. The first polynomial among the GIs is just the polynomial 1, but the other ones are up for grabs. We don't know what they are. But the idea now is that given this description, can we compute or at least estimate the geometric quantities for S just in terms of the algebraic quantities that describe A? And the extremely nice result is that yes, we can. And here is the first. Well, no, these are both theorems. The first one is okay. Is giving us estimates for the diameter in terms of the degrees, the lowest degree of these polynomials that appear in here. Once again, we have the n in this case is the dimension of the vector space V. So we have the dimension of the vector space appearing, so that makes them extremely not sharp, this inequalities, but it's some estimate. But really, the nice result is the second one. They tells exactly what the volume of the quotient is, and it is always, first of all, it is always a rational multiple of the volume of the sphere of that same dimension, right? So and the rational number is just given in terms of the degrees of these generators and the number of, in this case, P is the number of secondary generators, right? So if you know what this is, then you know how to compute exactly the volume of this. Once again, as a corollary, this means that the volume of any such space is a rational multiple of the sphere, which again goes in a direction into quantifying a vague concept that probably was already obvious from the algebraicity result, that, well, these spherical manifold symmetries should be somewhat rigid. Rigid in a sense that you really should not have like deformations, continuous deformations, like one parameter deformations of this spherical manifold summative. This is still not a theorem, but at least you can see that there is a rigidity. And this second result here is telling you that even if you have like one parameter deformations through through spherical manifold summative, then the volume of the quotient should remain constant, because it would not be allowed to go through irrational multiples of the sphere, right? So this gives rigidity, and what I would like to spend essentially the next and final, like, I guess, 5 minutes of my talk is to give an idea of how to prove this theorem. Here, I mean, like, it involves standard standard results used in invariant theory, and but the point is that it uses the vial law that I described before, and the point is like how you get there. It goes through looking at the Hilbert polynomial of the algebra A. The idea is simply that this algebra here is a graded algebra. So what you do is you can look at the pieces of the like higher and higher degree, and you can look at the dimensions. Okay, so this is just the part of A that has degree k, and you can build up this series. And it turns out, because of this extremely nice description of what A is that you have a very explicit formula for this polynomial. It doesn't really matter. However, what you can easily see also is that when you take this polynomial and multiply by 1 minus t squared, it turns out that what you're doing is now you're looking at the series that is counting in each degree the number of harmonic polynomials. So okay, now you have a series, an explicit series that tells you what they are like, how like the harmonic, so the polynomials with the zero Laplacian look degree by degree inside of the algebra of basic polynomials. And you just remember this fact that if you have a polynomial, a harmonic polynomial of degree k, and you restrict it on the sphere, well, then this becomes an eigenfunctions for the Laplacian of the sphere, right? So you have essentially this set here counts, by this I mean this is the eigenspace of the Laplacian of the sphere with eigenvalue this much. The point is that it only depends on k and on the dimension of the A. And well, so right, so what you get out of this is this, that this nice and explicit polynomial here contains information about the eigenfunctions of the basic eigenfunctions of the Laplacian, right? And now what you do simply is you take these two series and you look at them at how they explode at t equal 1. So when t becomes 1, they both explode, and they explode with a certain power. So you can look at the Laurent series at t equal 1, and essentially the idea is you just compare the first term in the Laurent expansion of the two terms. And this is what I'm saying here. We look at the first term in the Laurent series of these two series here, and on the left-hand side, well, you have an explicit thing. You can really compute it, and it's no problem. There is a factor of 2. I forgot here. The factor of 2 here, it doesn't really matter. On the right-hand side, what you get is exactly the term. You see, what you're counting essentially is how the number of eigenfunctions of the Laplacians goes to infinity. So here is where you use the vial law, and you get essentially just the ratio of the volume, just the volume of X divided by the volume of the sphere. and that's it. You compare these two, and you bring home, the result. Now, this like again, this was very well known, like definitely in the case of in the homogeneous case, in the case of finite group actions. In the case of finite group actions, the volume of X divided by the volume of the sphere is just the order of the group. So the way they phrase it in invariant theory of finite groups is that you can read the order of the group out of the Laurent expansion of this series. Very likely, it is also known. This stuff is also known for homogeneous, just more general group actions of compact groups. We have not found it, but maybe we haven't looked hard enough. So, of course, this holds also for homogeneous manifold symmetries, so for just the general case of representations of compact groups. But yeah, the point of this theorem is that this applies for a very wide case of spherical manifold symmetries. This being said, I want to conclude with a few open questions, since, as I was mentioning at the beginning, they were so fruitful last time I gave a similar talk, because that's where Emilio pointed out the Donnelly paper. So let me ask all of you these questions, and maybe you guys are able to solve those as well. So once again, the first open problem relates to something that I was mentioning already before about this rigidity and non-deformability of spherical manifold symmetries. Now, the idea of is that if you have a spherical manifold symmetry, there are obvious ways to deform. You just take an ambient isometry of the whole sphere or the whole space, and you just shift it, right? So these are the obvious ways you can change a spherical manifold symmetry. But here the question is, okay, up to those obvious rigid deformation, are there other deformations that are not obvious? Or equivalently, the moment you mod out by this group, is this set discrete? Once again, the idea would be to look at the corresponding, like look at this problem in terms of the Laplacian algebra. So instead of looking at this, you can just reformulate the problem in terms of deformations of Laplacian algebras. And this has been the object of some tentative work of mine with Ricardo, which seems to be a little bit too hard at the moment. But it is still is there. These are like, if this was true, this would be a great help to actually prove nice stuff, like proving that spherical manifold symmetries are just singular foliation, singular Riemannian foliations. So there is like essentially proving these would allow one to prove that the fact that two at the moment distinct concepts are actually the same. The second question is about, okay, we have used the Laurent series of this guy here just by looking at the first term and realizing the first term contained the volume in there. The volume of the base was contained in the first term of the Laurent series. Can we find geometric informations also in the other terms of the Laurent expansion? In the case of group actions, it is known that the second term in the Laurent expansion carries information about the number of reflections contained in the group. In the case of a manifold symmetry, this doesn't mean anything. So it would be interesting to see if there is some concept that generalizes essentially the number of reflections. The third problem relates back to the result proved by Kapovich and Lichak. And it goes to talk about symmetries, not smooth symmetries. So these are just, just continuous maps where the fibers are equidistant. And the point is that whenever you have a symmetry, Lichak and Kapovich proved that the fibers are C11 submanifolds, possibly with boundary. And also they proved that when you don't have boundary, then there are some neat properties. And they pretty much fell short of proving that the moment you don't have a boundary of in the fibers, then in fact the whole thing is smooth and in fact algebraic. So it feels like there is this huge gap between like many symmetries with fibers having boundary and symmetries that are algebraic. So like huge difference. This would be very interesting to know. And the final thing would be to understand, once again, we have a 1-1 correspondence between Laplacian algebras and manifold symmetries. Now, sometimes the manifold symmetries are homogeneous. And as of right now, there is no way of telling just by looking at the algebra invariant whether the algebra is coming from a homogeneous or if it is coming from a group action. Okay, so you're given a polynomial algebra. Is this the algebra of invariant polynomials for some representation? It is not known. If there was a nice criterion to determine when a Laplacian algebra is coming from a homogeneous manifold symmetry, these really would help a lot. For example, the classification problems of isoparametric hypersurfaces that I was mentioning at the very beginning, because one of the biggest points in that classification is understanding when a given isoparametric hypersurface is homogeneous or not, and essentially characterizing this type of algebras would give a neat way of attacking that problem, the classification problem of isoparametric hypersurfaces. And this being said, this is it. Thank you very much for your attention.
Yeah, many thanks, Marco, for a beautiful talk. Are there any questions or comments for Marco?
Hi, Marco. Hey, I got a question.
Hi, Adam.
Hey, how you doing?
Fine. How are you doing?
Good. Hey, so the first point on that last slide that you had of the open question, you mentioned that knowing this would kind of join the two concepts of singular mounting foliations and manifold symmetries. Is that obvious why that is?
It is not. It is not. This was actually an idea of Alexander. So essentially, the only thing that separates the two concepts is the moment you have a spherical manifold symmetry and you have a fiber, all you need to prove that it is a singular Riemann foliation is you need to find for every vector tangent to your leaf, to your fiber, a smooth vector field that is tangent to the leaves at all points, right? And the idea would be the following: you consider this let's say we are moving along a path, right, inside of the curve, and for all these paths you have these slices, right? Now these are just the normal spaces to your fiber at all these points. And essentially, on each of these guys, you have the infinitesimal manifold symmetry. You have the infinitesimal foliation inside of it. And so in so all of these guys, you have a one-parameter family of vector spaces with the foliations and the quotient space is always constant, and it is always equal to, well, essentially it is the tangent cone of the manifold of the quotient space at that specific point, right? So you have here you have your leaf, here you have the point in the quotient that projects your leaf, and in here you have a tangent cone, and this is exactly the tangent cone they all project to. So the point is that this is exactly a situation where you have a one-parameter family of spherical manifold symmetries, all with the same quotient, and essentially on the same vector space. You can just you can identify all of this. Right. If this was true, so having this, if this question was true, then what you would have is that the fibers, like all the changes along these fibers, is just some rotation. It's just some element of SOV that is just moving and just permuting, not really permuting, just moving around your fibers. So the idea would be that what you have is that at each stage on this one parameter family, you have your leaf that is kind of moving around. And you have to remember that all these leaves belong actually to the same global leaf, global fiber. Mm-hmm. And essentially knowing that this is coming from just a group action moving, having this group action is exactly what would allow you to construct these vector fields.
Ah, I see. Okay. Okay, thank you. Yeah, good talk, by the way.
Thank you.
Is this known for the homogeneous case?
No. Not that I know. No.
Any other questions or comments for Marco?
Can I ask something quick? Ciao, Marco.
Ciao.
The estimates that you had at some point involved, like the spectral stuff, I guess, involved the dimension of the top space. And you said that that's an undesirable feature, right?
Right.
I was just trying to understand whether it's clear that one should be able to avoid it, because if you fix a sphere of a given, or if you fix a quotient space like this X, is it clear that it can arise as the quotient of something that has a bound on a dimension? Or could it be that if you have a very strange X, it has to come from larger and larger and larger dimensions?
Yes, so right. You can clearly see it already when X is is an interval. Even the case of intervals of pi over 2, you have like you take your arbitrarily big sphere and write it as a spherical join of the two subspheres. You have an action of, let's say that is the spherical join of Sn1 and Sn2, right? You always have the action of SO n1 plus 1 times SO n2 plus 1. The point is that, let me do it like this.
Yeah, but that's going the other way, right? I'm saying if you have it's an example of a space that is coming from all sorts of quotients, right? From all sorts of top spaces.
Yes, yes, yeah. Oh,
and you find an X that only comes from spheres of sufficiently large dimension. Like as you said, the interval is coming from everywhere, right?
Yes.
Then could it be that there are some X's that appear that only arise if you consider ambient spaces, ambient spheres, which are sufficiently large dimensional? I mean, possibly no, but I'm just...
I mean, like, well, a sufficiently large dimension, like the moment you have something that arises for all possible spheres, well, in particular, it arises for spheres of arbitrarily large dimension. Probably I'm missing. So you're asking, let's see if I am understanding, right? You're asking, is there a quotient, is there a known quotient that you know it can arise from infinitely many spheres?
No, basically what I'm asking is why is it natural to expect that the class of spaces X that arises as that target map from a spherical manifold symmetry why should it be independent of any restrictions on the dimension of the originating sphere?
Well, because we know, okay, already in the homogeneous case, right? A recent paper of Ricardo with Alexander, Christian Lange, and Claudio Gorozki said that the diameter has a universal bound. So the moment you have a group action, right? The moment you have any group action, the diameter has a lower diameter bound that does not depend on anything. It doesn't depend on the dimension. It doesn't depend on anything, right? So that is the type of result that we're going for. So we're trying to find like a diameter bound that are as independent on the dimension of the sphere as possible, right? And it would be great to have stuff maybe even just dependent on the lowest term on the lowest degree. Like it would be great to have a lower diameter bound only depending on the lowest degree of an invariant polynomial, of a basic polynomial. Then the problem would be to bound that degree, like to find an upper bound for the degree. This would give a universal lower bound for the diameter of any quotient of any manifold summary. This would be the idea.
Okay, thanks.
All right, so let's thank Marco again for a very nice talk.